Good morning, everyone, and welcome to this lecture. In this lecture, we are going to start with and end with electric current. So we are going to do electric current in one shot, and I think this could be done. So we start with electric current. We already have an idea of what is electric current. Yes or no?
Yes, sir.
What is electric current? The rate of flow of charge is known as electric current. We all know this.
Yes, sir.
The time rate or the rate of flow of charge, the rate at which the charge is flowing, is known as electric current. Yes or no?
Yes, sir.
Now, whenever we talk about electric current, we can talk about two types of electric current. I mean, in two different ways. One is the average current. What do you mean by average current? One we can talk about is average current, and the other one we can talk about is instantaneous current. Do we know this? Yes or no?
Yes, sir.
What, sir? You know this?
Sir, average current is total charge per total time, and instantaneous current. Instantaneous current is current at any instant.
Total current, average current is total charge which has flown through a particular cross section divided by total time. And instantaneous current is the derivative dq by dt, the rate of flow of electric charge dq by dt. Instantaneous current is the current at any particular instant. Do we understand this?
Yes, sir.
What type of current? Small thing that you must remember about current. Current is one of the fundamental quantities. The dimension of current is m0 l0 t minus 1. Do we know this? Yes or no?
Yes, sir.
What type of quantity is electric current? Scalar or vector?
Scalar, sir.
Current is a scalar quantity. Even though current has a magnitude, it also has a direction. Current is still treated as a scalar quantity. Do we know this? So I'll give you 2 minutes to note everything down. Current has a magnitude, current also has a direction. Whenever we talk about the direction of current, we are talking about the conventional direction of current. And what do you mean by the conventional direction of current? The conventional direction of current is the direction of flow of positive charges. And positive charges will always flow from a point of higher potential to a point of lower potential. That means the conventional direction of current would always be from the positive terminal of the battery to the negative terminal of battery. Outside the battery, it will be same as the direction of electric field. But actually, what is happening is inside the conductor, the actual charge carriers are electrons, and electrons are actually moving in the opposite direction. Do we see this?
Yes, sir.
But whenever we talk about the direction of current, we will always talk about the conventional direction of current. So current has a magnitude, current has a direction, but it is still not a vector because it does not obey vector law. Do we understand this?
Yes, sir.
Okay. Now, even though current is flowing in a conductor, the conductor The total number of positive charge and total number of negative charge remain same. Therefore, even though when the current is flowing in a conductor, the conductor still remains neutral. Do we understand this? The
Yes.
conductor remains uncharged. Whatever number of charges are entering one end of the conductor, the same number of charges would be leaving that conductor. Do we understand this?
Yes.
For a given conductor, the current will remain same even if the area of the cross section of the conductor might change. So if you have a conductor which has a different area of cross section at different points, just like the diagram that I have shown, even though this has different cross sectional area at different points, the current would remain same. Do we understand this?
Yes.
Anyone understands this? I'll give you 2 minutes to note it down. Note it down fast. Okay, then we can move ahead. Now, sometimes uh, you are asked to find out the average current, and you are given that n number of particles are crossing a particular cross-sectional area per second. The area is A. What is the current? So current is total charge flown divided by total time. So in this case, the answer will become N into Q into A, where N is the number of particles crossing the area per unit time per unit area. Do we understand this? Sometimes this N is given as per unit volume. In that case, you have to multiply it by the volume, or you can multiply it by V into A, where V is the velocity with which they are moving and A is the cross-sectional area. Sometimes it is given that a charge is moving in a circular path. An electron may be moving in a circular path. A proton may be moving in a circular path. And you have to find out the equivalent current. So equivalent current will be the charge which is moving divided by the time period. Time period is 2 pi by omega. So you can write it in different ways. Do we understand this? Now this has gone above our head saying bye bye. Are we there in the class or anyone is lost? Do we understand this? All these points. Questions are going to come straight away from these points. Do we understand them?
Yes, sir.
2 minutes you have to note it down. Also have a look at this. There are a lot of questions that are coming on information based in this attempt, assertion, reasoning. So all these points become very important. What are the current carriers in different types of bodies in solids? Who are carrying current? Current carriers are free electrons. In liquids, they are positive and negative ions. In gases, they are positive ions and free electrons. In semiconductors, will be doing modern physics after this. The current carriers are known as holes and free electrons. So just note them down. Now, the next heading is you just have to understand what happens in the absence of electric field. Now, in the absence of electric field, even if there is no electric field applied inside the conductor, which is a solid body, copper, silver, gold, whatever you take, all these metals, there are a large number of free electrons. These free electrons are moving randomly in all possible directions. Do you see? They are moving randomly in all possible directions. The speed with which they move is known as their thermal velocity or thermal speed, and this thermal speed is somewhat same as your root mean square velocity. As you can see, the formula is same. Do we see this formula? This formula is same as root mean square velocity 3 kT by m. Do we understand this?
Yes.
At room temperature, this speed is very high. 3 kT by mm is the mass of the electron. The speed is very high, 10 raised to the power 5 or 10 raised to the power 6 meter per second. But all these electrons are moving randomly, so their net average velocity is 0. If you take any particular cross section, if n number of electrons are flowing in this direction, there is no reason why n number of electrons will be flowing in the opposite direction. Therefore, the net displacement or the net velocity or the average velocity is 0, and therefore the current is 0. Do we understand this?
Yes.
So, do we understand this what I have said?
Yes.
Are we there, beta? Please tell me, are we there?
Yes, sir.
So the net velocity is 0. Therefore, the current in a conductor when there is no electric field is 0. Do we understand this?
Yes, sir.
Then we have got two more terms, and I hope you will remember these terms. These terms have come from that kinetic theory of gases. We had seen the mean free path. This is the distance traveled by a gas particles between two collisions. Here, instead of gas particles, these are electrons, and they are, when they are moving, they are colliding. So the mean free path is the average of all these paths traveled by all these electrons. Do we understand this? Mean free path. Do we understand this?
Yes, sir.
Then we have something known as the relaxation time. Relaxation time. Relaxation time is the time between two collisions. So these are the two terms that we can understand. In fact, these three terms we can understand from kinetic theory of gases. Do we understand these three terms? Thermal speed is same as your RMS speed of gas molecules. When these gas molecules are moving between two collisions, the time interval between two collisions. Do you remember that time? The time interval between two collisions, tau, average time between two collisions. It is now known as relaxation time. Do we understand this? So these are the formulae for all these quantities, and we can understand them by understanding that kinetic theory of gases. Do we understand this? Then let us see what happens when a conductor is subjected to an electric field. If you put or if you apply an electric field on the conductor, and how do you apply this electric field? You connect it to a battery of voltage V. If the length of the conductor is L, because of this battery of the voltage V, a potential difference V is established between the lengths between the across the conductor, and this creates an electric field. The direction of this electric field is in this direction. Do we see this?
Yes, sir.
Now, because of this electric field, which is magnitude wise can be written as V by L, because of this electric field, the electrons will start to experience a force, and then they will be accelerated in a direction which is opposite to the direction of electric field. Do we understand this?
Yes, sir.
Because of this acceleration, the electron will be moving opposite to the direction of electric field. There would be a net flow of electrons in the direction opposite to the direction of electric field, and therefore there will be a current flowing in the circuit. Do we understand this? Write it up till here. I'll give you 2 minutes. So now what we have seen is that whenever electric field is applied, the electrons will have an acceleration in the opposite direction. Because of this acceleration in the opposite direction, they will acquire a speed in a direction opposite to the direction of electric field. That speed or that velocity which the electrons acquire, this is the speed that which the electrons acquire when the conductor is subjected to an electric field. The speed with which they move now is known as the drift velocity Vd. Do we understand this?
Yes, sir.
Vd. This order of drift velocity is very less, 10 raised to the power minus 4. Remember that thermal velocity was 10 raised to the power 5 meter per second. The drift velocity is very less compared to that. Remember, this is an important fact. But because of this velocity, because of this drift velocity, the current flows in the conductor, and the value of this drift velocity, if you want to write in terms of vectors, it can be written as a vector multiplied by tau. Tau is the relaxation time. Do we remember this?
Yes.
The drift velocity can be written as minus EE by m into tau. Remember all these small relations, because all these small relations are going to make a large difference in your eventual results. I'll give you 2 minutes to give me the answer. To note this down. Well, these are the relations that you must remember. As you can see, there is a battery of EMF or voltage V that creates an electric field E. The length of the conductor is A. Drift velocity, the velocity with which the electrons move. A is the cross-sectional area. N is the number of electrons per unit volume. Remember this. I is the current. K is current density. We have not seen this word, but we will see it just now. Rho is known as specific resistance, or sometimes we call it resistivity. So rho, we will get through this term also. And sigma is known as conductivity. Conductivity and resistivity are inverse of each other. Even if you have not heard this term, you can write the definition. You can write the relation here. I is equal to NAEVD. Have you seen this relation anywhere? Have you seen this relation anywhere? I is equal to NAEVD. Okay, N is the number of electrons per unit volume. E is the charge of an electron. A is the cross-sectional area, and Vd is the drift velocity. Then you can write this drift velocity in different ways. I by NAE. I by A is J. You will get to know all these terms. Write them together so that we have everything together at one place. When you understand the rest of the terms, you will be able to make out the other equations as well. Right now, just note them down. Well, then let's move ahead. We have seen the basic relations. We will move ahead, and moving ahead, we must encounter one vector here. And that vector is known as current density. So we'll write the heading current density. We will see this vector, and then we will move ahead. Current density, J vector. Now, what is this current density or J vector? Current density is taken as a vector quantity. Current density at any point in space, the current density is the current per unit area. Current per unit area is known as current density. Whenever current is flowing or charge is flowing through a particular section, the current density of that section is the current per unit area in a direction which is perpendicular to the area, because this current density is a vector quantity. So current density is di by dA into n unit vector, where n unit vector is a vector which is perpendicular to the area, or this is the direction of area vector. Do we remember this area vector ka direction? Do we remember this area vector ka direction? Yes or no?
Yes, sir.
We had seen this area is treated as a vector quantity in physics. Current density is di by dA into n unit vector, where n unit vector is the area vector. So the direction of current density is in the direction of area vector. Or you can write this equation in this way also. Di is The small current flowing through the small section can be written as J vector dot dA. Do we understand what I have written here?
Yes.
If you take a small cross-sectional area dA, what is the current passing through this small cross-sectional area? That will be G dot dA. So the total current passing through any cross-section will be integral of J dot dA. Current density is a vector and its direction is same as the direction of area vector, or you can say it is the direction of current density is same as the direction of current. Do we understand this?
Yes.
Now the relation between current and current density is the number of is the current per unit area, and current is the current rate of flow of charges. The relation between I and J is same as relation between what? Flux and electric field. Do we understand this? It's the same relation.
Yes.
Both have area vector coming into the picture. Do we understand this?
Yes.
Everyone understands this?
Yes.
I'll give you 2 minutes to note this down. What type of quantity is current density? It's a vector quantity. Its direction is same as the direction of applied electric field and current density. Its SI unit is ampere per meter square. If J is uniform, cross-sectional area is same, then you can write magnitude of J as I by A, because angle becomes 0. Cos 0 is 1. Do you understand? It is same as that electric flux. We get this or not?
Yes.
Now I is equal to N A E into VD. So I can write current density is current divided by area. In that case, it becomes N E into VD. Do we understand this?
Yes.
Everyone understands this? Or vectorly, I can write current density as NE into VD. Direction of drift velocity. Remember, this is not the drift velocity. Do we understand this?
Yes, sir.
Everyone understands this? The other way in which I can write this current density as sigma multiplied by E vector. E is the applied electric field. E is the applied electric field. What is sigma? Sigma is the conductivity. Or I can also write J vector as E vector divided by rho. These are the different ways in which you can write this. Direction of current density will be same as the direction of electric field. We have seen that. Write down all these points and we will be able to understand them. All these terms. Up till now, what all terms we have understood? I, J, VD, E and V. Sigma and rho are the two terms that we have not understood. Don't worry, time will come when we'll be able to understand them.
Sir, 6 amperes.
Yes, we got the answer.
Yes, sir. 6 ampere.
So these are the complete list of formulae for everyone. Go through this. Give you 5 minutes. Go through this. Let me know once you are done. Then you can move ahead and write the next statement. And the next statement is known as Ohm's law. Ohm's law. What do you mean by Ohm's law? What do you mean by Ohm's law? Okay. Before going on to Ohm's law, have you noted down till here? Let me give you some important points. Then we will go into Ohm's law. Just write important points here. We will move on to Ohm's law. The first point is the direction of drift velocity for electron is opposite to the applied electric field. Do we understand this?
Yes, sir.
The drift velocity is directly proportional to the electric field. Do we understand this?
Yes, sir.
The drift velocity is inversely proportional to the area of cross section. Have we seen this?
Yes.
If the current is same, then the current is same. If the diameter of the wire is doubled, then the drift velocity will remain same. Remember, if the current is same, and we will give you, and I'll give you examples. Don't worry, just write it now so that you are able to understand what is going to come. I will give you questions and then it will try to make sense. Everything is coming from the formula that we have written. All the questions are going to be solved from those formulae. You just have to remember these formulae that I have given you. Have you noted down these formulae? Yes or no?
Yes, sir.
I hope you are not confused with the formulae. I'll give you examples of each and everything. Don't worry with the questions which is coming up. Drift velocity per unit electric field is known as mobility. I have seen a few questions come on what is mobility. Remember, mobility is drift velocity per unit electric field. I'll give you 2 minutes to note this down. Then again, these are points which may come as question in your exams. If you have a conductor which is charged, inside the conductor electric field is 0, yes or no? But if you have a conductor and you apply a electric field across the conductor has a large number of free electrons, then the electric field is not 0. Do we understand this? There is a difference between flowing charge and non-flowing charge. Do we understand this?
Yes.
Current density. See, if the current is constant, you can see current I is same. If current I is same, then current density is inversely proportional to the area. Do we understand this?
Yes, sir.
If the area is constant, then the current is directly proportional to current density. See, depending on which thing is given constant and which thing is variable, you will understand what relation is going to come. So we will see all these things that we have written in terms of question, and probably then they will be making more sense. So just note them down now. I'll give you 2 minutes. Well, again, points that you must understand it instead of writing. Drift current is very small, but the number of free electrons are very large, and therefore you have electric current. The propagation of current is almost at the speed of light and involves an electromagnetic process. You will say, sir, drift velocity is so less. If I switch the switch on, the light should take a lot of time for light to get switched on. But the propagation of current is almost instantaneous. As soon as you put the switch on, the light is switched on. Do we understand this?
Yes, sir.
In the absence of electric field, the path of electrons between successive collision are straight line, while in the presence of electric field, the paths are generally curved. Again, it's a question based on your knowledge. The free electron density, number of electrons per unit volume, is given by this formula. You can easily calculate this. If you want, you can remember the form. I don't think this will come. It will be a question involving a lot of calculations. Just note it down. And here is the question. A potential difference is applied to an X-ray tube is 5 kilovolt. The current through it is 3.2 milliamperes. Then the number of electrons striking the target metal is. Now you may feel that this is a question of X-rays, but this is not a question of X-rays. This is a simple question. Give you 2 minutes to give me the answer. So how are we supposed to do this? It is given that the current is 3.2 milliamps. Current is total charge divided by total time. Total charge is number of electrons multiplied by the charge of an electron divided by total time. So number of electrons per unit time, N by T, is simply I by E. You just have to divide I by E. What is E? Small e.
1.6 into 10 to the power of minus 19.
That was it. That is what you had to do. So what is the final answer? Final answer is option A. 2 into 10 raised to the power 16 electrons are striking per unit time or per second. This question was as simple, and this is how questions are framed in a JEE. Do we understand this? Do we understand this?
Yes.
Have we noted this down?
Yes, sir.
And comes the next question, and I'll give you 2 minutes to solve this one. A beam of electrons moving with a speed of 10 raised to the power 6 meter per second along a line produces a current of 1.6 into 10 raised to the power minus 6 ampere. the number of electrons in 1 meter of the beam is how much? So how are we supposed to do this? Current is total charge divided by total time. It's a beam of electrons, so N into E divided by total time. Now total time can be written as x divided by v, where v is the velocity. Now we have to find out the number of electrons in 1 meter, so your x becomes 1 meter. Do you understand this?
Yes, sir.
That is your answer, my dear friends. So from here I can find out the number of electrons in 1 meter, n by x. Number of electrons in 1 meter, n by x is I divided by EV. I was given as 1.6 into 10 raised to the power minus 6 divided by charge of an electron is 1 by 6 into 10 raised to the power minus 19 multiplied by 10 raised to the power 6, and that should have been your answer. And the answer coming from this calculation is 10 raised to the power 7 electrons are there in 1 meter of the beam. Do we understand this, or this has gone above our heads? Saying bye bye. Bye bye, I'm going. Bye bye, I'm going. Bye bye, I'm going. Bye bye.
Understood, sir.
Thank God, sir, that we have understood it, sir. That takes us to the next question, sir, and I hope that I will have better results in this one. An electron is moving in a circular orbit, circular path. Oh, what was the next question? In the Bohr's model of hydrogen atom, Bohr's model, the electron moves. Have you heard about this Bohr's model of hydrogen atom?
Yes, sir.
See, God exists. The electron moves around the nucleus in a circular orbit of radius something something. Something something. The time period is something something. What is the current associated? You have 2 minutes to show me the presence of God, Almighty, all powerful, omnipotent, omnipresent. 2 minutes starts now. Yes, option D is correct. God exists. I is equal to Q by T. Here it is moving in a circular orbit. Electron, the charge of an electron is 1.6 into 10 raised to the power minus 19 coulomb. Is moving in a circular orbit. The time period is 1.5 into 10 raised to the power minus 16. You multiply, divide, and you end up with the answer which is given here. God is great, and we have seen his greatness now. I hope this greatness continues in the next question. The next question arrives now. A copper wire of length 1 meter and radius 1 mm is joined in series with an iron wire of length 2 meter and radius 3 mm, and a current is passed through them. The ratio of current densities in the two wires is, and you have 2 minutes. Option B, 9:1 is correct. You know, current density J is I by A. Here I is same. Yes or no? So current density in the copper wire divided by current density in the iron wire will be area of cross section of iron wire divided by area of cross section of copper wire. So this is radius of iron divided by radius of copper whole square. The radius are in the ratio 3:1. Therefore, the current density will be in the ratio 9:1. Do we understand this, or it has gone above our head? Saying bye bye.
Understood, sir.
Pakka, sir?
Yes, sir.
Then comes this. As I said, we have written a lot of points. We have seen a lot of formulae. to apply this formula and get the answer for this one. A wire has a non-uniform cross-sectional area as shown in the figure. A steady current I flows through it. Which of the following statements is correct? Option C, sir, is the right answer, sir. The only thing you have to remember is I is equal to NAEVD. Here I is same. Number of electrons would be same because same conductor. Charge of an electron is always same. VD is inversely proportional to the area of cross section. Less area, more VD, more area, less VD. The only option matches is option C. Do we understand this, or this is going above or at saying bye bye?
Understood, sir.
Pakka na, sir?
Yes, sir.
Then, sir, this is the next question, sir. Again, it only depends on whether you understand the diagram, the formula that we have written. In a wire of circular cross section with radius r, free electrons travel with a speed Vd, it is V. When a current I flows through the wire, what is the current in another wire of half the radius, same material? The drift speed is 2V. Option C is the correct option, my dear friends. I is equal to NAEVD. Same conductor, N is same, charge of an electron is same. So I will be proportional to A into VD. Do we understand this?
Yes, sir.
So I2 by I1 will be N2, sorry, N2 is same, A2 V2 divided by A1 V1. You can put the values and I think you will end up with the answer I by 2. Do we understand this? Yes or no? No or yes?
Understood, sir.
Next question arrives in style. A potential difference of V is applied at the ends of a copper wire of length L and diameter D. On doubling D, the drift velocity becomes. So, the potential difference is same, the length of the wire is same, D is same. What happens to the drift speed? I is equal to NAEVD. Current I does not change. Do we understand this? Length of the wire is not changing. The current does not change. Yes or no? So the drift speed will remain constant. It does not depend on VD is EE by M into T by 2. Do we remember this? Yes or no?
Yes, sir.
So it does not depend on your diameter, and therefore the value remains same. It does not change. Do we understand this?
Yes, sir.
Okay. Next one. Questions are framed in different ways so that you understand them from all possible avenues. A current flows in a wire of circular cross section with free electrons traveling with a drift velocity of V. If an equal current flows in a wire of twice the new radius, what is the new drift velocity? Now the answer has changed. I is equal to N A E V D. Current is same. Number of electrons are same. E is same. So the drift velocity is inversely proportional to the area of cross section. Yes or no?
Yes, sir.
Radius becomes twice. So the drift velocity will become 1 by 4 times. Yes or no? Yes or no? So the correct option is option C. Do we understand this?
Sir, what is the difference between before question and this question, sir?
I don't know. Let's see both the questions together. Yes. A potential difference V is applied at the ends of a copper wire of length L and diameter D. On doubling the diameter D, what happens to the drift velocity? A current flows in a wire of cross-section area with free electrons traveling with a mean free velocity of V. If an equal current flows in a wire of twice the radius, what is the new mean drift velocity? And the question is very evident. What is the relation between the two? What is, why in one case the answer is here and why in the other case the answer is different? Yes. In one case I am writing drift velocity is inversely proportional to area. In the other case I am saying drift velocity does not depend on the area. Why? Hmm. VD, if you look at the different formulas of VD, it was half EE by M into tau. VD was lambda by tau. I is equal to N A E V D. These are the 3 or 4 formulae that we know about this. In one case, I am saying that it is inversely proportional to the area of cross section. In the first case, I am saying a potential difference of V is applied. How are these two things related? You have to understand the question. Here, the potential difference of V is applied on a copper wire of length L. Now, V by L becomes what?
Electric field.
V by L becomes electric field. The electric field is constant here. Do we understand this?
Yes, sir.
Electric field is constant here. Now look at the options. Electric field is constant here. Do we understand this? Electric field is constant.
Yes, sir.
Electric field is constant. Do we understand this?
Yes, sir.
We understand this. Electric field is constant. Therefore, the drift velocity cannot change. Do we understand this?
Yes, sir.
Here, it is given in terms of current. Equal current flows. Equal current flows. Current is equal. Then the drift velocity is inversely proportional to area. Do we understand this?
Yes, sir.
Good that you have brought this thing up. So you have to we have to take each and everything in totality. How the question is framed, in what way it is framed. V and L are same. I said when I was explaining the question, V and L are same. Did I say that or not? Electric field is same. Therefore, the drift speed is same. Okay? We get this?
Yes, sir.
So be careful in such questions. Be careful about such questions, because that is how the questions will be framed, and if you make a mistake, you are done. Two wires A and B of the same material having radius in the ratio 1:2 carry current in the ratio 4:1. The ratio of drift speed is what? Option A. Again, this question will not have controversy. NaEVD, same material. So this is same. E is same. I is proportional to A into Vd. Yes or no?
Yes, sir.
So I can write I1 by I2 as A1 V1 upon A2 V2. Once you put the formula correctly, you will get, I think, 16:1. We understand this?
Yes, sir.
This one is the next one in line. In a neon discharge tube, 2.9 into 10 raised to the power 18 neon plus ion move to the right each second, while 1.6 into 10 raised to the power 18 electrons move to the left per second. The charge on the electron is this. What is the current in the discharge tube? It has taken a lot of time for you to solve it, but that is the correct answer. Positive charges are moving from here to here. Positive charges are moving from here to here. How many positive charges?
2.9 into 10 to the power of 18.
2.9. Forget about 10 raised to the power 18, because all the answers are in the same unit, so I don't have to worry about the unit. Negative charges are moving from here to here. Now, negative charges moving from here to here. 1.2. Forget about 10 raised to the power 18. It is same as positive charges moving from the other side. Yes or no?
Yes, sir.
So the total positive charges that are moving is 3.1 multiplied by the charge of an electron. Yes or no?
Yes, sir.
This is the current towards right. So you have to multiply 3 by 1.6. So it's not 3. 2.9 plus this is 4.1. So you have to multiply 4 by 1.6, and you will end up with something 0.6466, and that is your answer. You have to do it quickly. Taken a lot of time to do it. Do we understand this? How this is to be done?
Understood, sir.
That takes us to the next heading, which is known as Ohm's law. Ohm's law. You must be knowing what is Ohm's law. Yes or no? Everyone knows what is Ohm's law. Yes or no?
No, sir.
You don't know Ohm's law? You've never heard about Ohm's law? Surprising.
Heard, but forgot.
Don't have anything to say. If the physical conditions of the conductor remain same, the temperature, length, and so on, the current flowing through the conductor remains constant. I is proportional to V. You cannot say that you don't remember Ohm's law. This is crime. This is murder. You have studied your 12th standard. You have done your board exams. You have given 2 attempts of JEE Main in 12th. You have given 1 attempt of JEE in after this a drop year. And if you tell me that you don't remember Ohm's law, V is equal to IR, or V by I is equal to R. R is a proportionality constant. This is like doing 7 murders at the same time and still roaming free. You can't say you don't remember Ohm's law. I don't have words to describe what have you just said. Anyways, V is equal to IR, that is Ohm's law. If I draw a graph between V and I, it would be a straight line like this. If I draw the graph at different temperatures, the graph would be like this. When temperature increases, resistance increases, and therefore R1 in this case will be more than R2. Remember, Ohm's law is not a uniform, Ohm's law is not a universal law. Lost for words, I don't know what to say. Anyways, write this so that you can move ahead. Remember, Ohm's law is not a universal law. It's not valid for all bodies. Those substances which obey Ohm's law, they are known as ohmic substances, and these graphs are only for ohmic substances. These graphs are only for ohmic substances. If the substances are non-ohmic, these graphs are not valid. Well, substances or bodies which do not obey Ohm's law, they are known as non-ohmic bodies. Crystal rectifiers, thermionic walls, all these bodies, they do not obey Ohm's law. So if they do not obey Ohm's law, their VI curves is not linear. Then they have two types of resistance. One is known as static resistance. The static resistance is the relation between voltage and current at a particular voltage, that is static, while the rate of change of voltage, because the rate of change will be different. So the slope of graph at any point, the slope of VI graph at any point will give you the dynamic resistance. Static resistance and dynamic resistance, they are both shown in this diagram. At this point, if I find the static resistance, it will be the resistance between this point and O, the origin, 0. So this is given by the tan theta of this, 1 by tan theta of this. For dynamic resistance, we find the slope of the graph at this point. Do we understand this?
Yes, sir.
Give you 2 minutes to note this down. Okay, then these are the graphs of some other types of bodies which are non-ohmic. The first one is the tetrad wall, not in your course. The second one is diode, it is in your course. The third one is semiconductor, it is in your course. The fourth one is torch bulb. You may or may not do this, and draw it fatafat and let me know once you are. The next heading that we are going to write is the resistance of a conductor. What is the resistance of a conductor, or resistance of any wire, or resistance of any body? Electrical resistance we are talking about, the property by virtue of which it resists any flow of charge through it or any flow of current, that is known as resistance. It depends on size, shape, geometry, and temperature of the conductor. The SI unit is volt per meter. Volt per ampere, the dimension is given. It is directly proportional to the length. It is inversely proportional to the area. It depends on the material. So R becomes rho L by A, where rho is a constant. This rho is known as the resistivity of the conductor. Resistivity of the conductor, or you can also call it specific resistance. It also depends on the temperature. R at temperature T will be R naught into 1 plus alpha into delta T, where R naught is the resistance at 0 degrees Celsius. R naught is the resistance at 0 degrees Celsius. T is the temperature. Alpha is the constant which is known as temperature coefficient of resistivity. We have seen this. We have seen this
Yes.
formula previously also. Where did we see it? Obviously, you don't remember it anyways. You can draw the graph between temperature and resistance. The graph is also there. The graph is also there. For conductors, alpha is positive, and for semiconductors, alpha is positive for conductors. And for semiconductors and insulators, alpha is negative. That means for conductors, their resistance increase with temperature, but for semiconductors and insulators, their resistance decreases with temperature. Do we understand this? Yes or no?
Yes.
Well, here it is given for all the types of bodies what happens when the temperature is increased. There is something known as a superconductor. If you decrease the temperature of a conductor, its resistance will decrease, and at one particular temperature, which is known as the critical temperature, its resistance becomes zero. That temperature is known as the critical temperature, and then the conductor becomes a superconductor. Okay, for metals, alpha is greater than 0, so their resistance will increase with temperature. For solid non-metals, it is 0, it's practically independent. For semiconductor, it is negative. For electrolyte, it is negative. For ionized gases, it is negative. For alloys, they have a small positive value. For superconductors, below a certain temperature, the resistance is 0. Do we understand this, or you can just note them down fast?
Sir, in the previous slide you have given.
In the previous thing, what?
Nothing, sir.
Then we come again to this diagram where the resistance is given as a function of temperature. As you can see, this is the graph. R0 is the resistance at 0 degrees Celsius. If R1 and R2 are the resistance at T1 and T2, R2 by R1 will be in this ratio. Do we understand this? The
Yes, sir.
value of alpha will be given by this. This is the formula if temperature is less than 300 degrees Celsius. If the temperature is more than 300 degrees Celsius, actual formula is like this. Do we understand this?
Yes, sir.
Here we are assuming that alpha and beta are constants. We will also see the case when alpha and beta are not constant, but I hope you understand this, yes or no?
Yes, sir.
Okay. Give you 2 minutes to note this down. Then the next point that we are going to understand is resistivity or specific resistance rho. Resistance is rho L by A. If length is 1 meter, area is 1 meter square, so you can define resistivity as the resistance of a wire of unit length having a cross-sectional area of 1 meter square. The SI unit of resistivity is ohm meter, and the dimension is given. The formula for resistivity is this one. So resistivity is a property of the material of the body. It does not depend on the length, size, or shape of the body, but it depends on temperature, and we will see that temperature dependence. And this is the formula of resistivity with temperature change, and you can see this formula is same as the dependence of resistance on temperature. In fact, resistance changes with temperature only because resistivity changes with temperature. Do we understand this?
Yes, sir.
So you can write this formula in the differential form as d rho by dt is rho into alpha, and if you solve this, this is the actual formula of resistivity. Similarly, the actual formula of resistance is like this, but if the temperature change is small, you can write the formula in the form that we are given: RT is equal to R naught into 1 plus alpha into the delta theta. But the actual formula looks like this. Do we understand this?
Yes.
The actual formula is like this, but you can write it in that way. I'll give you 2 minutes to note it down. Then we come to the small thing, conductance. Conductance is the reverse of resistance, and conductivity is the reverse of resistivity. We understand this?
Yes, sir.
Give you 2 minutes to note this down. Then we can see how resistance of a body may depend on between which to which point you are applying the potential difference, or between which point and which point you want to measure the resistance. Let us say this is a cubical conductor, and you connect the conductor like this. You connect the conductor, this is the conductor, cubical conductor. You connect the upper face with the lower face, and this is connected to a battery. The length of this side is A, the height is B, and the depth is C. Can you find out the resistance of this conductor if I connect it like this? I'll give you 2 minutes to give me the answer. So how are we supposed to do this? As you can see, this phase, you can find out the area of this phase, that becomes the area. Remember, the resistance is given by rho L by A. L is the distance between, is the length of the conductor. In this case, the value of L, which is the length of the conductor, would be this distance. This distance would be the length of the conductor. The wire is connected from the top face to the bottom face. The length of the conductor is this height. So B is the length of the conductor, and the area of cross section of the conductor is the area of the upper surface or the lower surface. So the resistance of this wire, if it's connected in this way, it will be rho into B divided by A into C. A into C is the area, and B is the length of the conductor. Do we understand this?
Yes.
This is how you can find out, depending on how you have connected the conductor, you can find out the resistance in various cases. Let me take the example of this one. Now, if I connect the conductor like this, conductor is like this. Now I connected this end with this end. I've connected a battery between these two facing faces. In first case, I had connected the top with the bottom to a battery. Now I've connected one end here and the other end here. What is the resistance of this conductor now? I'll give you 2 minutes to give me the answer. In this case, the resistance is always equal to rho L by A. Here the length will be A and the area of cross section would be BC. So the resistance in this case will be rho A by BC. Do we understand this?
Yes, sir.
Similarly, in this case, can you tell me the answer for this case? What would be the answer in this case if I connect it like this? Now I connect the forward end to the back end. Forward end to the back end.
Rho C by AB.
In this case, the resistance will be equal to rho into C by AB. Do we understand this? Yes or no?
Yes, sir.
Okay, that is great. So that we can move ahead, and we can move ahead to the next thing upon which questions have come in this session only, which is known as stretching of wire. The next session is known as stretching of wire. What happens when the wire is stretched? What happens when the wire is stretched? Now remember, when the wire is stretched, one thing of the wire will remain same. What will remain same? The volume of the wire remains same. Do we understand this?
Yes, sir.
A1 is the initial area of cross section. A2 is the final area of cross section. We must understand that A1 into L1 will be equal to A2 into L2. Do we understand this?
Yes, sir.
Do we understand this?
Yes, sir.
The initial resistance of the wire R1 will be rho L1 by A1. The final resistance R2 will be rho L2 by A2. And A1 into L1 will be equal to A2 into L2. From here you can find out or get these relation between the resistance of the wire before and after. Yes or no?
Yes, sir.
I'll give you 2 minutes to note this down. Similarly, you can note down in this fashion also. If the length is increased by n times, the resistance will increase by n square times. We can get it from that relation. If the radius is reduced by 1 by n times, the resistance will become n raised to the power 4 times. Do we understand this?
Yes, sir.
Okay. Well, then we can write this shortcut as well. If you increase the length of the wire by x%, remember this x has to be small, less than 10%, then the resistance will change by 2x% because the resistance is proportional to L square. Do we see this? That comes from that error and measurement wala chapter. D delta R by R is equal to 2 times delta L by L. Do we understand this?
Yes, sir.
Everyone knows that? So I'll give you 2 minutes to note this down. Have you noted it out, beta?
Yes, sir.
Okay, then I will wind off today's class here. We have done a lot of things in today's class, starting from what is current, what is average current, what is instantaneous current, current density, vector quantity, sigma, rho, resistivity, resistance. We have seen a lot of relation between a lot of things. I want to give you time so that you can go through all these questions, because if a question comes from electric current, if it is not coming from circuits, it is going to come from this part. And I've seen question coming from this part and they are very pretty simple. So I would like you to go back home, have a rest, see all the things that we have written. Some things have overlapped. Resistance, what is resistance, rho L by A, on what all factor it depends on. Go through them, read them peacefully so that you can remember them in the examination also. We will continue, and we could not finish it today because still things are left. So probably in the next class, by the next class, maybe tomorrow, we would try to wind up this chapter on electric current, because there are still a lot of things left. We had only covered resistance and resistivity. We have to still do some more questions on resistance and resistivity, and we'll have to see the electrical instruments as well. So we will do that in the next class tomorrow. Take care. God bless you all. Bye bye. Have you understood what you have done in today's class?
Yes, sir.
Go back home, read what you have written, and you already have the sheet. Solve questions from that sheet. I'll see you tomorrow. Take care. Bye bye.
Thank you, sir.